This is a video that's going to introduce you to section 9.2 in MyLabs Plus about linear regression. Our targets in this lesson are we want to be able to find out, learn how to find the equation for the regression line and then use that equation to predict y values if we're given a value of x. Now just to note, all of what we learn here can be done using technology. So for those of you who have the graphing calculator, the TI-83 or the TI-84, you're going to find on the PowerPoint posted in Blackboard the tools or the steps necessary to be able to use your calculator to find this regression equation as well. But of course, we're going to need to know how to compute it by hand. So we've learned how to calculate the value of the correlation coefficient, and we've learned how to test to determine if there's a significant relationship between the two variables. Those are the things we learned in lesson 9.1. What we want to now do is come up with an equation for a line that can be used to make predictions. Now the line isn't just any line, it's known as a regression line or a line of best fit. It's a line that goes up for the most part through the center of all the data points and helps to describe the pattern of the data points on that scatter plot. Once we get the equation of this regression line, like pictured here, and we'll learn that that equation is going to be in this form, then we can use that regression equation and plug in a number for x and find a corresponding y value, so we can make predictions. Now, what we have to note though is that line does not fit perfectly with the data points. The only time that would ever be the case is when the correlation is exactly equal to +1 or exactly equal to -1. So that line is making some errors in its predictions. Now, hopefully they're small errors, but there is typically some amount of error that's made in the prediction that the line will make. That error is known as a residual. And a residual, you'll notice, is just the observed y value minus the predicted y value. So use, for instance, this point right here. The blue point on top is the actual observed piece of data. But for that particular piece of data, the line would predict that the y value is actually less. So these 2 points have the same x coordinate, but the actual observed point is higher than the predicted point. So the line is actually under-predicting the value of y for that particular point. On the other hand, look at this point here. You can see that the actual observed point in blue is sitting below the line. The point on the line above it with the same x coordinate is actually up greater than the observed. So in this case, the line is over predicting the value of y. So you can see clearly, though, that those points aren't far from the line, so the error in the predictions doesn't appear to be that great. We do need to know that there will be error in the predictions, and that error is called the residual. So we want to learn how to calculate that line of best fit. So the regression line is the line for which the sum of the squares of the residuals is a minimum. Let me demonstrate what I mean by that. Say this is our line of best fit, and just for simplicity purposes, say I've got these 3 points in my data set. If I were to draw in all of the errors in red, these red lines represent the amount of error in each of those predictions. If I then were to form a square, so all sides the same length, for each of those residuals or errors, my squares would look something like that. The location of this line of best fit is in a place where the sum, in other words, add the sum of the areas of those squares is as small as it possibly could be for any line I might fit to the data. Let me demonstrate with a line I might fit to the data that doesn't fit the data well. Okay, so I'm going to draw in another line, but clearly not one that describes the pattern of the points very well. Now, if I draw in all my residuals for my 3 data points for that line in green, and then make the squares using those residuals as the side lengths, those first 2 squares seem to be rather small, but look at this guy here. He's got a very big square that is formed by his residual. If I add up the areas of these 3 squares in green, those areas will be much larger than the 3 squares in red. So that's what we mean when we say that the least squares regression line, that's another name for it, line of best fit, regression line, or least squares regression line, is the line for which the sum of the squares of the residuals is a minimum. Okay? Now, we mentioned previously that the equation for our line of best fit is going to look like this, and we've seen this in previous algebra courses, except we're putting a little hat over that y, and that just means predicted y. We call that y hat. Y hat equals mx plus b. M is the slope and b is the y-intercept. We're going to learn how to find that slope and y-intercept here by hand. Okay? So first you see a very tedious formula. One very similar, well, it's different formula, but it's similar in its tediousness for finding slope. The formula for finding y-intercept isn't as tedious. It's just going to be take y bar minus slope times x bar. Now, what are x bar and y bar? Y bar, we know x bar is just the mean, but it's the mean of the x's. Y bar is then the mean of the y's. And one thing that we want to note is on every regression line we might fit to every set of data, the point that has coordinates x bar, y bar will always sit on the line of best fit. That point has a name. It's called the center of gravity. So if we compute our regression equation correctly, and then we substitute x bar into our equation, we'll find that the predicted y will be equal to y bar. Okay? All right, so we're going to revisit our GDP and CO2 data. We want to find the equation for the regression line for the gross domestic products and carbon dioxide emissions data. So we can see from our formula that we need a lot of different sums similar to the sums that we needed for correlation. We need the sum of the x's, we need the sum of the y's, we need to take every x and multiply it by its corresponding y to get these values here, and then get the sum of those. That's the sum of our x, y's. We need to get the sum of our x squareds. So for instance, this 2.56 is just taking the value of x and squaring it. The 12.96 is just taking its value of x, 3.6, and squaring it, and so on. And then we need to get the sum of the y squareds. So I did for you here, and these are all my sums displayed here at the top. Now when you're finding an equation for a regression line, you have to find the slope first. Okay, then you can find the y-intercept. So here's my slope formula. I'm going to plug in everything I now know. N is the number of pairs of data that we had. We had 10 pairs of data. The formula then says multiply that by the sum of the xy's. The sum of the xy's is this 15,573.71. Okay? Then the formula says to subtract the sum of the x's. Well, the sum of the x's is 23.1. But you need to multiply that sum according to the formula, by the sum of the y's. Well, the sum of the y's that we previously computed was 5,554. So there's the calculation for my numerator portion of my slope. Okay? Now the denominator. The denominator says I need to take n, which again is 10 pairs of data, and multiply by the sum of the x squared. The sum of the x squareds was 67.35. And the formula then says that I need to subtract the sum of the x's and then square that answer. So again, the sum of the x's was what was in blue, the 23.1, but I need to square that number. Okay? Now, if you do this with me on your calculator to verify you are entering it correctly, you should get a numerator equal to 27,439.7, and you should get a denominator equal to 139.89. So then when you divide that numerator by that denominator, you should get a slope equal to 196.151977. That's the slope of our line. Now we need our y-intercept. Here's the formula for y-intercept that we gave you previously. We need to take y bar, which is the mean of our y's, and subtract the slope times x bar. Okay? So the mean of our y's, we need to add up all of our y's and divide by 10 since there are 10 of them. So we already know that the sum of our y's was 5,554. We need to divide that by 10 to get the mean of our y's. Then the formula says I need to subtract my slope, which I now know is 196.151977, and that needs to be multiplied by the mean of our x's. Well, once again, we know that the sum of our x's was 23.1, and there were 10 of them, so we need to divide by 10 to get the mean of our x's. When we compute that, if you compute that with me, you should get a y-intercept b equal to about 102.2889. So now we have two very important values that are going to be used in our regression equation. Here's our b, and here's our m. So our regression equation will be y hat equals mx plus b. I'll round to 3 significant digits. So 196.152 times x plus b. I'll also round that to 3 significant digits. That's 102.289. There's my regression equation. There's the equation for my line of best fit. And if I graph that line with my data on a scatter plot, I can see that it fits pretty well. Now to sketch the regression line, you can use any two x values within the range of your GDP. So somewhere in between like 1 trillion and 5 trillion. Pick a number for x. Substitute that number into your regression equation to find the y and plot that point. Do that with a second x value. Pick a number for x, plug it into your regression equation, find the y that goes with that x and plot that point, and draw a straight line between them. And that's how we fit our regression line to our data. But we also want to be able to make some predictions using our regression equation. So here it is again, and we want to use this equation to predict what we would expect the carbon dioxide emissions to be for that particular gross domestic product value. So I've got three different numbers we're going to substitute into our equation. First, $1.2 trillion. Now remember, X was in trillions. So what that basically means is we're just going to substitute 1.2 into the regression equation. So I just rewrote this regression equation and replaced X with 1.2. When I substitute that value in and calculate that on my calculator, this model would predict 337.671. So basically what that means is when the gross domestic product is $1.2 trillion, the carbon dioxide emissions are expected to be about 337.671 million metric tons. And again, million because our CO2 values were in millions. Okay? I'm going to do the same thing to make a prediction for $2 trillion in gross domestic product. So I'm going to substitute 2 in for X in my regression equation and calculate the value of Y hat. In this case, we should get 494.593. So when the gross domestic product is $2 trillion, this line would predict that the carbon dioxide emissions would be about 494.595 million metric tons. Hopefully you're getting the hang of this. My third prediction, 2.5 trillion. So I substituted 2.5 in for X, and when I calculate the value of Y hat, my expected Y, I get about 592.669 million metric tons. So when the gross domestic product is $2.5 trillion, this model would predict the carbon dioxide emissions would be about 592.669 million metric tons. Now notice these values I've carried to three significant digits, but you'll carry them out according to the instructions in MyLabs Plus. So these prediction values are meaningful though only when we're using the model to predict values that lie within the interval of gross domestic products in our data. Our gross domestic products in our original data set ranged from 0.9 to 4.9. So we want to use this model only to predict values for X, values for Y, for X's that are between 0.9 and 4.9. What we're doing is called interpolating. We don't want to substitute a number like 6 in for X because 6 does not lie within the range of GDP values that were in our data. And so that's called extrapolating. And we don't ever want to use our models to extrapolate because this equation that we've been using here for our line of best fit was created using a data set that goes from 0.9 to 4.9. We don't know how that equation might change if we extended that data set to values outside of 0.9 and 4.9. So we like to interpolate, which is to pick numbers that lie within the interval of X values in our original data set, but we do not want to extrapolate. We do not want to substitute numbers in that are less than 0.9 or greater than 4.9. Let me know if you have any questions.